Okay, good morning. So today see as we did last time. Okay, it doesn't matter. Sometimes I switch U with C. Let's think of a concentration. Okay, some pollutant. And then I want to show you something which, again, I like very much. Does not appear in all books, but it's also very simple and very instructive. So let's do the Upwind method. For this case, which the molecule is like that, so it reminds us how to do the problem. Okay, and let me write something for you. Now, I'm going to show you something which I think is a few things that are very interesting and are good exercises on the computer. So remember we did forward, let me put it like this, so I don't have to write everything from the notes. Forward, backward, say Taylor polynomial expansion, as you wish to call it. I call it sometimes expansion, but truncate, it's basically a Taylor polynomial. And then we have this. Okay. Now here's where the fun starts, is here. This is wrong. No, let me write it the way it's getting ahead of myself, sorry. Okay, so, excuse me, little, okay, this is a constant, okay, and put like this, constant positive, which is upwind, right? The wind is blowing left to right. So look, as we get used to notation, the way I communicate and stuff like that, I have done nothing, no big deal here. Okay, what I did is I've expanded this derivative, that derivative, this is this and that. I'm evaluating, so this is, I'm evaluating the PDE on the grid. Okay, that's all there is. So this is basically okay, so what I'm saying here, nothing, no big deal. Just with a convenient notation is PDE evaluated at the grid point is this. And this is exact because I'm not paying too much attention of either the tail of the Taylor series expansion, or this could be the error of the Taylor polynomial and so on. Okay? Now, let's play with these guys. Okay? So let's play with these guys. So note that, okay, all trivial, but just to get our notation to help us, if C is the solution of the PDE on the grid point, I can exchange derivatives. Okay, those of you who did the PDEs course with me last semester, we did this a lot, and actually we borrow. Sometimes we change derivatives with an error and so on. Here it's actually, at this point, it's exact. Okay? That's when we do reduced modeling. If some of you look, we did the course, or look back in the PDEs course. No big deal. Okay? So I can also, I'm assuming everything is, for now, I'm assuming everything is, say, smooth, so I can do this. Okay, so I can take more derivatives. I'm not doing, right? Nothing more. Just there's one step in between, but very simple, right? So to some extent, it's like the derivative in time solving the equation doesn't matter. Why am I doing this? So it looks like I'm just doing this simple stuff for nothing. But why am I doing this? I'm doing this because, bless you, I'm doing this because it's the English, the course is in English. You can say, instead of "saw would you," can say "bless you," right? So we're good international in all aspects. Also, not numerical PDEs, was health for everybody, international health. So, why am I doing this? Because I want to get these two guys here together. And let's see if now you already know, we had like already some classes, if you can guess a little bit what I'm thinking. Why do I want to get these two guys together? Think of some things I said last class. Not to cancel. No. It's okay, fine. I mean, sometimes we want to cancel to get rid of some terms of higher order, but no, not to cancel. And this thing, it's simple, and it appears, I think, in very few books. I mean, Levesque at some points, one of his books, Conservation Law, mentions this. Not all books mention this. It's simple, and it's very useful. And I actually learned this for the first time, not in the book, but because in my graduate course, a great numerical analyst, Masha Berger, who was actually a plenary speaker, I think, at the last international conference, she mentioned this in class as a nice trick. So what do I want to do? Remember, I mentioned Upwind last class. You probably don't remember everything I mentioned last class because we've got to study and some stuff are new. Remember that I did ODs and I showed to you numerical damping. And I think I said that we were going to see some methods in Upwind had numerical diffusion. Okay, I mentioned this quickly. I don't know if you remember. You probably remember. Numerical diffusion. So what am I hunting for? What am I looking for? I am trying, and we will succeed, to try to rewrite this as having a diffusion term, like from the heat equation. This guy is already a guy that looks like the a term from the heat equation, diffusion term. This one is not. But with this, I can sort of do a trick of saying, okay, I can maybe, somehow, to first order, replace this guy by this guy up there, because right now, and you see at the end I will say, so pay attention. Right now I'm saying that C, I think of it as a solution of the wave equation, okay? And later on I'll say, okay, now think of C of a solution of another PDE, and it's called the Modified Pde, which is very useful for us to understand what our numerical method is doing. And you will eventually verify this on the computer, as you'll see, as I'll mention to you, okay, at the end of the class. So look at this. So then I can write, let's see if I can keep all this together. Maybe, I use maybe two a bit too much of a large handwriting up here. I should have made it smaller, but okay, it's my problem. So if I substitute, okay, so let me put this here. Look at this. 1 substitute 1 in here, and we can write the following. Let me see if I can do a little smaller handwriting so it looks. This is where is it? Okay, being a little pedantic, but it's just for the good. So to have this right, I think I do. So look what I did. And this is I think it's very useful, very simple. So I manipulated this, okay? I kept what I don't want to pay attention, I kept it in this trash can, which I'm not truncating yet. So this is, to some extent, looks like exact. I throw this away. And now I can think of this. And I can say, look, this is my numerical method. This is what we put in the computer. Okay, so let me put it different colors. Hope it appears sometimes in the video. So the red is the numerical method. And here's an interesting way to think. And you will see on the computer, we see this very well. So this is a numerical method, which I'm going to program. Okay? And I'm programmed this. I think I'm programmed this to solve this. But depending on choices of your grid size, you will see, as I will explain more and more in just a second, that the solution has sometimes unexpected behavior. For the upwind, then I'll mention other methods for you for the same equation. For the upwind, I will see that my solution has some diffusion. Remember last time that I mentioned to you that we had the advection diffusion equation. Sometimes you switch off the diffusion and you see diffusion still on and say, oh, there's a bug. That's my first reaction. And you chase the bug, I programmed something wrong. I didn't switch diffusion off, but you see the solution has diffusion because it has numerical diffusion. And if you turn on the diffusion, you have numerical diffusion together with physical diffusion. And it will look like the diffusion is exaggerated. Here it is, the numerical diffusion for you, due to the upwind. This method is performing actually better for this PDE than for this PDE. Can you see why? Because if I think that I'm solving this PDE inside the yellow thing, it's higher order. And look at this. Now this is a very nice, cool thing. Look at this. This is a numerical kappa, numerical diffusion term. That depends on my grid. Oops, here. That depends on my grid. This is usually called the current number. The current number appears sometimes written like this. I'm just writing it like that just to remind you, I mentioned this last time, that it is a ratio between the true speed and the numerical speed. Okay? And there's a Cfl condition usually for these things, which is this has to be, current number has to be smaller than 1 and so on. And you will see it here also, without doing the Cfl, which is the current Friedrichs Levy, right? 3 famous people he actually found this condition trying to prove more, I think if I recall, sort of existence of solutions, and the condition was actually a condition that also amounts to numerical stability. Okay, and many proofs sometimes of existence. I mean, things just like you see in ODEs, Picard iteration. It's a little bit looks like a numerical method. You discretize things to prove convergence to some extent, and then you get the solution, right? So look at this. If the current number, let me write this sigma better, it deserves to be written better. This current number, okay, if the current number is greater than 1, we have negative diffusion, and I won't say this here in the table, but I mean, if those of you who are doing PDEs now or will do, negative diffusion means you have a ill-posed problem. Everything grows exponentially. The diffusion, you can show that things decay exponentially. Negative diffusion, which is negative diffusion or doing the heat equation backward in time, is an ill-posed problem because high frequencies grow in an unbounded way, okay? So look at this. If you have negative diffusion, pooh, round off error, everything is going to blow up. Your method is unstable, okay? Negative diffusion. So therefore, you see that the current number, that the numerical speed has to be greater or equal to the normal speed. And you will see on the computer that actually if you want to run a profile without numerical dissipation or diffusion in this case, the best case is to put sigma equal to 1 or very close to 1. Depending on the problem, some people like to put it a little smaller, want to have a little bit of attenuation due to, but this depends on the problem. For this simple problem here, you can put sigma equal to 1 to eliminate this term. So this advection diffusion equation, you see this is an advection diffusion equation, okay? Is called also, let me put it here, the modified equation. In some books, very few books, you would see modified equation because it's not the true equation I had in mind, but it's a modified equation that expresses in a clear way what the numerical method is doing. So it's a bit funny, right? We're trying to solve something continuous. We build up something discrete, which helps us to solve the continuous guy, but to understand what the discrete dynamical system is doing, sometimes when we can, it is convenient here to go back to this continuous model and see this higher order term, what it's doing, okay? So therefore, it's called the modified equation. That sort of best represents the behavior of the numerics. Because in other words of thinking is that the numerical method is sort of closer, because of this thing, see, to solving this PD than to solving that PD. Okay, and this simpler trick, you see this in the computer, the numerical diffusion in the computer. Okay, so the truncation error, if you think from one occasion or the other. So important fact. So let me put here. Fact. Current number sigma equal to 1. Let me put it like this. Kills or eliminates, kills not eliminates. Let me put it like this. At first order. I'm just protecting myself, saying this numerical diffusion or dissipation, diffusion or some sort of dissipation, right? Dissipation and diffusion could be different. Dissipation does not depend if you do a damped wave equation. dissipation does not depend on the Fourier mode, whereas diffusion depends on the Fourier mode. The decay is stronger the higher the frequency. Okay? This is a little bit more from a PDE. Not everybody, as I say, not everybody has done a more advanced PDE course here. The order doesn't, as I mentioned before, doesn't matter so much. But comments are comments, and of course, when it's just a comment like this, I will not expect you to have it on the top of your head. So diffusion as first order. Why? Because there might still, if I do a very long run or whatever, there might be still some damping mechanisms here, whatever, in the higher order terms. And you would see this for a longer run. Okay, but for a shorter time interval run, you put sigma to 1, and you do not see to leading order a numerical diffusion. Okay, that's what I mean, to leading order. Okay, so let me mention other methods. Okay, now I'm just gonna. So yeah, this is Levesque. This is one of the books, Levesque, around page 101, and so he mentions these methods. So let me write it for you because these are famous methods. I'm not going to deduce them, but I want you to have a feeling for them. So there's Lax Friedrichs, Upwind, Lax Wendroff, and there's another one, B. Mormon. I will not write. I'll write these three. So look at this. Methods deduced in different ways. Well, Upwind we already have. Okay, I won't write Upwind again just to save us time. Let me write Lax Wendroff. No, wait a minute. I think I mixed up two methods. Oops. Let me see. Lax Wendroff. Yeah, mixed up two. Sorry. Oh, sorry. I think maybe I can fix just here. Yeah, I did mix up, sorry. Oh, yeah. Okay, so look, the molecule of this one is like this. Right, Upwind, we know the molecule. It's like this. And this one, it's a bit like a centered scheme. Okay, or sometimes I also call it the case where it's called leapfrog, we jump, it doesn't matter. So look at this. I'm not going to deduce the methods. Lax, right, very famous, just a very super famous mathematician, right, with theorems and numerical methods. So he had these two methods, which are Lax Friedrichs, Lax Wendroff, very famous methods. In particular, were, I think, as I imagine, deduced for conservation laws. So I might mention, for those of you who haven't seen what a conservation law is from the PDE point of view, you'll probably be seeing this in either PDE's course you're doing right now, I would imagine, or certainly when you do PDEs in application with me, and I might mention quickly here as we go along. Yes, Masa? Of course, thank you. Thank you. We got to move in time. Thank you. I'm going fast and copy. Thank you. Let me double check now. See one. Thank you. I made mistakes on both of them because it's small in my notes. I think it's age also, not reading well. Boom. Yeah, thank you. So this is already a good point, as Master asked this question, that both methods are explicit. They're both constructed doing tricks with a little bit, in particular, I think Lax Wentworth, using the PDE and so on, monkeying around in a more sophisticated way as I did it here to get higher order terms. You see if current number appears here, and so on. But there's an interesting difference between Lax-Wendorf and Lax-Friedrichs. And I'm going to compare this, say, with Upwind, and let me actually compare both of them. Let me compare the two Laxes method. Look at this. Let me not say anything. Let me just write, and then we'll discuss. Okay? Let me remain in silence, and you try to figure out where I'm trying to go. What am I trying? Not only where I'm trying to go, what am I trying to contrast? Okay? So let me write as you go along. Okay. So Lax, let me put it like this. Lax-Friedrichs, okay, is like this. So let me use a little bit of notation from the notes. Is equal to something. Okay, I'm not going to write in detail. So this is the Lax-Friedrichs operator depending on the courant number. This equation, and here's the modified equation. Okay, so we get, and this is the important thing. Okay, and now let me do Lax-Wendorf, and I'm going to go straight to the modified equation. Okay, and now we're gonna go into something that maybe some of you have never seen. I don't know. I'm curious to know, but at least in the PDEs and applications course, we saw these two equations. From the more modeling PDEs point of view, where this is from a numerical point of view. So this parameter here, look, this parameter here, let me call it like this, is a numerical epsilon, right? Because it's epsilon as a function of delta x and delta t. Now, so what is the difference? So let me put it this way. Lax-Friedrichs and the Upwind are on the same sort of type of modified equation, which is different from Lax-Wendorf. Why? Because Lax-Friedrichs and Upwind have numerical diffusion. Boom. Okay? So here is, basically what we have here is numerical diffusion. Okay? Now let's see, which one, you guys now are buyers of numerical method, right? Which one in terms of numerical diffusion, so they basically are in the same sort of category. Both of them have numerical diffusion, right? Both of them, if I put the current number equal to 1, I switch off the numerical diffusion. Is this fine? Right? But which one has sort of a, you would say, has a stronger numerical diffusion? No, Lax Friedrichs does not have numerical diffusion. So wait, maybe there's something you haven't seen, Mas. Okay, I'm just talking about Lax Friedrichs. Sorry, the question was, I'm still playing the game as salesman, game of Upwind and Lax Friedrichs. Which one has maybe, to some extent, I'm not going to answer, or else I'm going to answer the question. I can sort of, I mean, let me ask this way. What is the difference in terms of diffusion qualitatively? Let's see if you know, the question is difficult because we're starting to exercise these questions. Qualitatively, between Lax Friedrichs and Upwind. Upwind is here. So what would you have to say, right? Because I want to stimulate in you guys the critical view of choosing things and then going to the computer, seeing it work. But what do you see? Look at this. Right? Here, sigma, and here, sigma squared. So to some extent, the diffusion of Lax Friedrichs varies more, more quickly to some extent with sigma, but sigma is smaller than 1, right? So this one, but on the other hand, here's delta x, and here's delta x squared. So it's higher order, right? So that's basically it. So it's higher order, so the diffusion, the whole diffusion would be smaller. But you see, to switch it off, I really have to use 1, right? And this is what matters. Now this one is what we call numerical dispersion. Okay, so I need to mention a little bit about numerical dispersion because those of you who did PDEs and applications with me last semester know what I'm talking about, right? It's a dispersive PDE. Some of you might not know. So just out of curiosity, who doesn't know what a dispersive PDE is? Okay, all the rest knows, right? So basically, it's something which has to do with Fourier modes. So let me mention a little bit about this, okay? So let's go over here. So, okay, I have it in the notes, good. Let me contrast, oops. Let me contrast these two equations, okay? So let me maybe leave some space. I don't think I'm doing a good job here. So we call, in PDEs, a dispersion relation is the following. When we have a linear constant coefficient PDEs, it's very easy to solve these PDEs using Fourier analysis. That is Fourier modes. So I can basically say, look, pick a generic Fourier mode, which is like this. Say, let's see the notation I'm using here in the notes. Okay. Okay, so this means this is the amplitude of this sort of sinusoidal, it's like a sine plus a cosine, doesn't matter actually, that travels to the right, say, okay? And this is basically the temporal frequency and the spatial frequency. So this is also called the wave number. Okay? And if you plug this in here, you get that omega k, this is the dispersion relation. This is what's called dispersion relation. We get okay? And therefore, we transformed a PDE into sort of an algebraic relation between the temporal frequency and the spatial frequency. You plug this into here, right? And you get that the solution is going to be, this is just the amplitude of this Fourier mode, e to the I k x minus omega k over k t. Okay? And this is called the phase speed. Okay? Being the phase speed being the speed of the, say, the crest of the wave. It's a phase, right? The crest of the wave would be the phase, say, 0 to pi, whatever. Okay? And then if we're solving the whole solution, since the system is linear, we can do a Fourier series if it's periodic conditions, or a Fourier transform, which means sum over all these guys. Because it's a linear problem, you do the superposition of all Fourier modes. But here we just need to look to a generic Fourier mode. And this is the amplitude of this generic Fourier mode, which has spatial frequency kappa, k, not kappa. Okay, now look at this. This gives me the first thing, two things to mention. If epsilon is equal to 0, which is this, the unidirectional wave equation, then omega k over k is equal to u, which is what we know. It's the speed of the unidirectional wave equation, right? And does not depend on the Fourier mode. Okay? So fine. This is constants. All modes with the same phase speed. Now, let me do the heat equation, which is what I mentioned there. See, I'm gonna get a free ride here. Now, if I have u equal to 0, just for the fun of it, look what I have. I have this. So I have a, let me put it like that, selective decay of Fourier modes. Why selective decay? I'm not going to do the details. You do it because if I don't have u, if I switch off my wind, and I have just the diffusion, my advection diffusion equation, this I with the I, whatever, and then you see the decay rate in time will depend on the spatial frequency. So higher frequencies, which are basically higher frequency, which are, right, faster, higher, smaller wavelengths, will decay faster. So in particular, sometimes a little bit of numerical diffusion is used almost a little bit as a filter to kill out higher frequencies terms in a numerical way if they're unimportant mathematically, physically, blah, blah, blah. Okay, sometimes people put that. So, and then you can see that if you switch the sign, all modes, if for negative diffusion, all modes will grow with a rate k squared, and it's unbounded. So as k goes to infinity, it's unbounded. So that's why the negative diffusion or the backward heat equation is ill-posed. Okay, that's typical stuff. So this is okay. So, but now here, if we just use this for what we did here, then this is numerical diffusion. And numerical diffusion, if this epsilon is numerical, this is numerical diffusion, and it damps faster high frequency, as I just mentioned. Okay. Now numerical dispersion. Okay, so if I do the same thing for now this equation here, which is actually a famous equation, is the linear Korteweg-de Vries or aka KdV equation. Okay? This equation is dispersive. Here, if we do the same thing, the dispersion relation is uk minus epsilon k, cubed. And let me put here a capital C, which is the typical notation for phase speed, depends on k, which implies that PDE is dispersive. Okay? So let me repeat. This is the linear KdV, right? So here I'm just talking about PDEs. Just think the epsilon is some constant. If you do the dispersion analysis, which is plug this mode here, little c, into this equation, you're going to get this dispersion relation, which is the relation between frequencies, temporal and spatial. You get the phase speed is given by, this is by definition. And actually in this case, divide this by k. Look, the phase speed is going to depend on k squared. So therefore, Fourier modes propagate with different speed. But this is a numerical methods course. And since this is a numerical methods course, this epsilon is a numerical epsilon. And since it is a numerical epsilon, where did I write this? It depends, here it is. It depends on delta x and delta t. So as I play with my grid size, I am playing with either numerical diffusion or numerical dispersion, depending if I'm using one of these methods. And I better know how to use them according to the method. So what a numerical dispersion does, let me put it here, is this, or the diffusion. And this is something that I want you to do, to see on the computer. As you'll see, I'll send you things by email for you to do on the computer. So one exercise is this. You put a Gaussian pulse. It looks like right? It's a good example of waves. And why the Gaussian pulse is very useful? It's because not only it's a smooth C infinity pulse that looks like a wave in the ocean, looks like a wave in an acoustic system, right? It's also good because the Fourier transform of a Gaussian is what? A Gaussian. So it's very easy to picture in our minds. And a fat, wide Gaussian in physical space is what kind of Gaussian in Fourier space? It's a skinny Gaussian in Fourier space because it doesn't need much modes to represent it. And the other way around. If it's a skinny pulse, thin pulse in physical space, like a wave that goes very fast up and down, it needs high frequencies to represent this rapid variation. So it's a wide, fat Gaussian in Fourier space because it needs a broad spectrum to represent it. So it's a very useful, right, object to play with if you're playing with waves on the computer. So if you're solving Upwind or Lax-Friedrichs, this is what numerical diffusion will look like. Eventually, depending on the grid size you use, you will see this numerical diffusion. Because look, if you're solving the wave equation, you should see this guy move as a traveling wave without changing its shape. Right? If you're solving this equation here, right? This equation, as we saw in last class, this is just a translation to the right with speed u. But on the computer, you will see a translation to the right, but with diffusion. which is numerical diffusion. If you use then Lax-Wendroff, which is dispersive rather than diffusive, what will you see? You will see on the computer this. You will see this oscillatory tail starting to form and increase, and this is a sign of numerical dispersion. Okay, high frequencies falling behind. Okay, and and here at the bottom of the notes, well, I have some time here. Okay, let me mention some of this. Let me mention this. I mean, let me write this here. It's so small in the notes. So we know the following. No, it's not even a review, just from PDEs, okay? Theoretical PDEs, not numerical PDEs. It's not a review, it's information for you. Because if I called it review, it would be dishonest, in particular because the dispersive part is not easy. So if this guy here, we can show in the course numerical PDEs, we show that actually this can be written, and actually both of them can be written like this. Oops, I forgot something here. Sorry. Where for the heat equation, okay, and then if we do the numerical dispersion, let me write this and then I'll comment afterwards, sorry. In this case, is more non-trivial to show. So that's why this is more like information. Okay, squeezed here in the back. So what am I saying here? Let me. So this is PDE information for you, okay? Okay, so let me get my hands full and now explain. So what have I done here? So it's basically giving you PDE information so that you understand better, even better, what you're going to be doing on the computer, okay? So the first part, it's up to here. I hope it was kind of simple. You let me know anything, right? It's just that I was showing what is a dispersion relation. I forgot to say that actually we mentioned also the jargon of the field is that we say numerical dispersion relation. Okay, so for example, the problem then, if the numerical dispersion relation like this guy here has dispersion, but the equation does not have dispersion, then it's spurious dispersion because the PDE is the wave equation, no dispersion, like here, no dispersion. But the numerical method has dispersion because of this guy. Okay, so there's the dispersion relation related to the PDE, and the numerical dispersion relation related to the numerical method that you're trying to solve the PDE, right? And here in this course, of course, we're going to be interested in both. So So, okay. So now to understand even a little more, in particular also this and what's going on, now it's just information from PDEs, which the first part we actually do in the theoretical course of PDEs and applications. The second one I just mentioned because it's more non-trivial is this. If you solve this equation, which is the heat equation, so I'm switching off the transport. I'm switching off the advection part, which, just to simplify things, or if you want to think, you're putting yourself in a moving frame. Okay, you can change coordinates here so that you eliminate this guy because you're in a moving frame. No big deal, okay? So then the important thing is to see the heat equation. The heat equation, we see how to solve it. Many of you have seen this independent of taking the course with me or not, that the heat kernel is a Gaussian, right? And actually, so the heat kernel is a Gaussian. Here it is. Okay, here's the epsilon, which makes the Gaussian fatter, quicker, or not so quick because it's the diffusion coefficient here. And this is the solution, right? The solution is if the initial condition is an F, right? Then it's this convolution of the Gaussian with this F. And actually, this is a good way to see too, which is something we'll mention in a second. You probably heard this. If you have, let's think of heat now, since it's a heat equation. If F is discontinuous, which means I have a wire which is part hot, part cold. So it has a jump, boom, at time 0. At time 0 plus, as soon as I switch on my time watch, the solution is C infinity because a Gaussian, right? It smooths out the jump in a very quick time, right? As soon as time 0 plus, right? You see what I'm saying? Because if I formally can differentiate this, I'll be differentiating this guy too. So these things we see, this one in detail in the PDEs and applications course, and here, I mean, take it as an information. At one point, if you want to see this in more detail, one idea is also even looking at one of my classes, which are in Portuguese and English for the PDEs course, but you don't need it here. Here, I want you just to have the information and know how to handle it, okay? Which is if you have a jump here, this guy, see, this guy immediately smoothed it out at time 0 plus. And this Gaussian has total mass 1, right? And that's why Gaussians, these things appears also in probability theory, right? Heat, diffusion processes and so on, has total mass 1. And actually we show in the course in PDEs that if you come from time and you let time go to 0, you recover the initial condition because this guy goes to like a delta function, right? It becomes skinnier, 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 larger and larger amplitude and mass 1, right? For dispersion, it's more complicated, right? First, it's more complicated even because a special function will appear in the middle of the business. This is the Airy function. And the thing is, the story is, which is not, I mean, just so you know how the story goes, but it's not that simple, is that if you get this guy here, which is the dispersive term, you put this guy in here, you're going to get a k squared, and you try to integrate the Fourier transform, it's not that easy, right? And you will end up dealing, if you recognize things, you end up dealing with the Airy function, which is a function, which is a special function, and you cannot write the solution in closed form. You have to see it as an integral, and you have to do asymptotics with the integral. That's how you do it for say the linear KdV, water waves. You saw this in PDEs. But this function here, if you plot the Airy function, if you look at books for the Airy function is a function like this. That if you do the asymptotics, here it decays exponentially, and here it decays, it's namely the tail of the Airy function, like a sine with a algebraic decay, blah, 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 if you do the asymptotics, right, for blah, blah, blah. And you see the kernel now for the linear KdV, the kernel is the Airy function. And as time goes on, You see this guy grows. So that's a little bit the mathematical mechanism for making this tail appear behind your wave solution. And it can be shown, not trivial, it can be shown that this guy also has total mass 1. Look, the amplitude, if time goes down to 0, right? Not doing backward in time, just checking the initial condition. This becomes large, blah, blah, blah. So this also can go to sort of a Dirac type of mass, right? Gives you back the initial condition, blah, blah, but in a more complicated way. So there's two ways of seeing why this dispersion creates this tail that grows behind a wave. A more mathematical way is because the kernel has to do with this special function, which is oscillatory behind its front. This we call the front, and this we call the tail, or sometimes also called the coda, right, of the wave. Another way of intuitively seeing why this tail forms behind the wave is because you look at this and you will see that, high frequencies and so on. Okay? Even though another thing, the KDV, the linear KDV has a problem. It's a long wave model, blah, blah, but it has also a problem that for very large frequencies, the speed can change sign, even though it's a model for things propagating to the right. But this is a little bit of a mathematical artifact. It's usually small frequencies. But okay, I mentioned this a little more, explain a little better these things when we do the PDEs and applications course. So the other important thing, I'm good in time, because the other important thing that I want to say today, right, is the following. Right? Which also, one of the aspects has, well, let me say it first. So there are two very interesting problems that I want you to do on the computer to see the math theory working on the computer, and even without you knowing all the details of the math theory. For example, how do I deduce this, whatever, but I want you just to understand how as a tool. Right? This one, even in the PDEs course, I don't do it in all detail. This one I do, this one I just give references and okay? But the important thing here is to understand what's going on with a mathematical background and, of course, seeing things working in practice. So look, now, let me put it this way. Now let's put a discontinuity by hand. Note that the linear PDE does not produce a discontinuity. And in this case, actually, I can put it in the context of a shock. A little bit like a shock. Let me put it quote unquote. Okay? So, do you know what I'm saying? So I'm saying, I'm basically doing this. Look. Now let me go back to, say, U, maybe. U, T plus Cx. U0 versus okay, some of you, I know that some of you know what I'm talking about. Some of you maybe not yet. But this is basically our linear wave equation. And this is Burger's, called Burger's equation, where you see the speed depends on the solution. So this is a nonlinear equation. And actually in the technical case, it's called a quasi-linear equation. That's a detail. I might do a little quick review of this afterwards. Okay? So maybe even in a little while, since I have time, just to get everybody on the same page, as we say in English, right? So this equation produces a jump. This one doesn't. But to test numerical methods, I can put a jump by hand. Okay, and like what? I can say, look, I can say this, look, I'm going to try to solve this problem for this. For a Heaviside function, this is like more than a wave. We usually call this a front, right? This, of course, a ridiculously simple model, but it's a good to test numerics. Would be, say, like in the weather prediction, we have a cold front or a high pressure coming in, right? So it's a fast change of things, right? Of course, this is not the model used, but if you want to test sophisticated models, you should start testing it in this situation. This silly equation, remember the test problem, so useful, right? I also want you to test the test problem. So this is so useful. It's a simple problem where we can understand things. I am putting this solution with a discontinuity by hand. On the computer, can you do a discontinuity? No, right? I mean, a vector at each point needs a value, but if you have a very fine grid, you might have two very nearby points. It's going to be a slope. It's almost like it's continuity, right? So we can't do discontinuities on the computer, but we can do something that, if we have a very fine grid, points nearby, it's basically discontinuity, and you will see all this mathematics working before your eyes in practice, giving you intuition, which is very important. So here it is. So this guy will form a discontinuity doing the dynamics. This one, I'm now going to put a discontinuity. Why? Because I want to see how these two mechanisms, which are regularizing mechanisms, will deal with the discontinuity so that maybe, then with nonlinear cases, we can test more sophisticated methods like Lax-Friedrichs, Lax-Wendorf. There's a whole family of methods designed to capture shocks, right? Which I don't even know if I'll talk in the course, maybe it could be something to be reading in the future. We'll see, which are Eno methods and so on. So look at this. So now, the heat equation, I already kind of convinced you that it would regularize a shock. In the PDEs course, we see this in all detail, right? But it will regularize a shock, not the course. It will regularize the shock, the discontinuity. How? Well, because of the Gaussian, blah, blah. It's like, just think of this as a temperature, as I mentioned, right? So if I put this on the computer, and I will want you to do this, whoever is watching can do this on their own, is that this profile, as it evolves, okay, in time, so it's a front. So think of a front where it's infinite in this direction, right? It's coming so big that I don't care where it ends, right? The temperature front or the high pressure front. Let's think of a temperature front. The weather is going to become hot, okay? So the temperature is going to rise suddenly, very quickly over a few hours. And then if I am solving this problem, this is the orange is the initial condition. If I am solving this with upwind, right, I will see my solution doing this. Okay, so this is a regularization. This is a diffusive. It's a diffusive regularization of the jump. You can do this mathematically, I mean, if you're doing just theory of PDEs, but here it's actually a numerical regularization, which might still be okay, because it's like, this is a fast transition, which is actually what happens in practice. If this is just a few minutes or hours, right, that's the temperature change, it might still be okay. And you will see that if you play with the sigma, the Courant number of the method, you can make this yellow curve here steeper or less steeper, depending on the Courant number. right? If current starts getting closer to 1, you get closer to the jump. You're never going to get the jump, even because you cannot start with the jump, because you cannot, right? Okay, so this is the numerical diffusion, and this is good to see also how numerical method deals with a shock. I assume people, right? I'm not an expert in shocks and conservation laws in this regard of shocks and so on. Dan Marquezin, Alexei here at IMPA does some of this, but this is a way to test your numerical method with a baby problem where you put the discontinuity by hand and see how it handles it. And then if you see this, you understand. You understand from the modified equation. Okay? Now, now if we do the same for a diffusive problem, either for a diffusive problem or with a diffusive numerical method, what will happen? So this shock, this jump should again propagate like that, because I'm not solving this equation or this equation. I'm solving just the wave equation. So the solution should be like this. Okay? But then, what will happen if I use then Lax-Wendroff, which is higher order and so on? If I use Lax-Wendroff, it does not have numerical diffusion. It has numerical dispersion. And dispersion, as I mentioned, is associated with oscillations. Sometimes a tail forms behind, which is the case here for if I have a Gaussian. But here, it will be slightly more subtle, and it will be like this. My drawing is not going to be very good, but it's qualitatively, okay? It's going to be something like this. Can you see it from the back? Can you see it, Lucas? Okay, so it's going to capture the jump in oscillatory fashion. Okay, it looks a bit like sometimes we see in Fourier-Gibbs effect, but it's not quite the same. Okay, and here, there's two very important things from the theoretical PDEs point of view. Here, if you let the epsilon goes to 0, this guy becomes steeper, 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 and eventually goes to the jump. And there's some exercises we did in the PDEs and applications course where you see this explicitly. Okay? And this is usually called a viscous shock, because this epsilon here from the heat equation, for those who do fluids, plays a little bit the role of viscosity. Right? So this is called a viscous shock. So it sort of looks a little bit like, right, the burgers with a term here, which sometimes is also called the viscous burgers. Okay, so this is the viscous shock. Now here, the dispersion, the zero dispersive limit was something that people proved in PDEs much later than things. It was more, scientifically speaking, it's more recently. People like in the 70s, whatever, 60s, 70s, or 80s, were proving things, is that this solution of this converges to the solution of the other one in a strong sense, right? We can say this, but this one, the solution converges in a weak sense. What does that mean in the weak sense? In the weak sense is that you sort of somehow have to write things in a more sophisticated way, actually in an integral form, right? An integral form. And why? So this is interesting stories for you to know. Of course, and actually you're going to see some of this. You're going to get a feeling for this in the computer, but it's more difficult mathematical technology, and not even the PDEs course. I do it, I just mentioned it, is that as epsilon goes to 0, the scale of these oscillations becomes smaller and smaller and smaller, so it becomes more and more high frequency. But the amplitude, in particular I should draw a little better, because the amplitude I think here is a little higher. Okay, I'm exaggerating so that you can see it from the back. Okay, and it's a little bit in the spirit of the area function. It sort of decays. Okay, this amplitude does not go to 0 fast enough, so it becomes faster and faster. So it becomes something a little bit like this, say. So faster and faster as epsilon goes to 0. But this and the amplitude does not decay to 0 fast enough. So it has to be done it's a weak limit, And you can think of this weak limit, quote unquote, and I mentioned this in the PDEs course, in the spirit of the Riemann-Lebesgue lemma. Right? The Riemann-Lebesgue lemma is when you integrate things of the type f cosine nx dx with this n going to infinity, this goes to 0 because there's a cancellation, right? Intuitively, quickly speaking. So this is in the same spirit. So you will numerically see the same thing. So if you use one numerical method, you will see this. If you use the other numerical method, you'll see that in the shock capturing. So this is also in the jargon of numerical PDEs. I could basically say that these are, I could call this shock capturing features, right? How does it capture the shock? In a diffusive way or in a dispersive oscillatory way? Mathematical theory, PDE theory, tells us that diffusive way, the convergence is more, it's in the classical sense. The other one is more complicated. It's in the weak sense. There needs to be cancellations and so on. But still one can use one another depending on, again, depending on what you want to do with your numerical method, what you want to show, and so on. Okay? So these are different types, okay, of regularization from the PDE's point of view. Different types of regularization because of regularizing a bad property of your solution, for example, not having a derivative. But from the numerical point of view, it's a different type of numerical property. Numerical diffusion, numerical dispersion, right? And it's to you to choose depending on your problem, okay? So let's see here what I should do. In the interest of time, and at the end I want to mention something. So let me ask you to see. I mean, when I talk about Burger's equation, who has seen Burger's equation and know that it forms a shock in finite time? Also, just the people who took PDEs with me. So let me show this very quickly in just a few minutes, because then it's good. Method of characteristics, because then I'll prepare for another lecture, which I'll talk about using the method of characteristics numerically speaking. Okay? So very quick then, let me do it. So I'll do this really in a very sort of a specialized, quick way, right? Not as I do in the PDEs course, because so for the interest of time, okay? So let me do this. U of t plus c u of x equals to 0, okay? So what we're thinking is that we have here x, we have here time. It's not numerical, right? But we saw by inspection last time that I can write this. This is just chain rule. If I am thinking that I am on a moving frame, okay? So sort of a moving frame, or following a particle, if you want, also in the fluid sense, a little bit like Lagrangian. So if I do this, and if, whoops, I have something wrong here. Sorry, okay. This is just the total derivative is this by definition. It's equal to 0 from the PDE if dx dt is equal to c, because then it's the PDE. Well, this is my moving frame, and this means that, look, this is dx dt equal to c, right? Look at the derivative like this, right? And this means that along these lines, the solution does not change, right? So if I do a 3D plot, x, t, u, n. These are called the characteristics. Okay? I know that my solution, so if I have a wave here like this, later on in time, it will be the same thing because this guy does not change along this curve. Right? This is what this is saying. This guy does not change along this curve of constant slope. Yes? That's the method of characteristics, right? And usually the characteristic systems, the characteristic system of ODEs for this case is basically where Z is the same thing as U. Okay. Now, if we go to burgers, it's the same thing, but now dx dt is equal to U. Right? So therefore, this means, let me see if I can do a good drawing. Let me put my pulse like this. Put another time here. Okay, this is my initial condition. These are lines parallel to time. But look what happens now. Here, the slope, this slope here, dx dt, was constant. But now, the slope is variable and depends on the size of the wave. So therefore, this guy here, so this guy here has a not so big slope, but this guy here has a very big slope. Oops, and it will cross at some point. And this is the critical time. This is space, time, u. This is then critical time, which we can calculate analytically, no big deal, where a shock forms. And basically the wave, if we do it on the computer, this wave, because this guy here is moving faster than this guy, eventually this guy will get very close to this guy and the wave breaks. This is a wave breaking model, which is it's simpler than a more sophisticated wave breaking model, which would be like that if we're talking about waves in the ocean. This can be done. I mentioned a little about this in the PDEs. In the PDEs course, we're not going to see it here, right? But this one here, right? This is a little bit the PDE doing a shock. So if you do Lax-Friedrichs or Lax-Wendroff for this equation, Berger's equation, you will see a different behavior when it gets close to shock. If you're using Lax-Wendroff, when you get close to this, you will see as a little spiky profile appearing here, which is an indication of what? Numerical dispersion, okay? And if you see this guy attenuating, it's an indication of numerical diffusion, okay? So these are basically how all these things connect, and knowing, of course, knowing PDE theory helps you with numerical PDEs, but also knowing numerical PDEs for those who are doing in a different order stimulates your intuition for when you go and study the theory in more detail, right? Because you're going to see these, I'm going to ask you to, you're going to see these things on the computer. And maybe I think this is a good time for, I want to still talk to you, but maybe a good time to stop the video. Thank you.